way transcranial direct current, or tDCS, typically works is that you apply electrodes over particular brain regions with the goal of increasing or suppressing the excitability of those regions. And that's how it's been done traditionally. The problem is that we know from past research that brain regions interact with other brain regions. There are excitatory and inhibitory relationships that cause brain regions to interact through really distributed networks. And the problem is that the way traditional tDCS has typically been applied, it doesn't really account for those network effects. So basically what we wanted to do was to see if applying tDCS to an entire network would have a greater effect than just to a particular brain region. What is currently known about motor excitability is that if you put an electrode on the scalp over the motor cortex, you can increase excitability in that region. What our results suggest is that instead of increasing the excitability of a particular region of the motor cortex, that you can actually enhance the excitability of the entire motor network, which you can see as increased excitability of both hands. And what this suggests is that it's possible to modulate entire networks, potentially to an even greater effect than modulating particular brain regions alone. When we use transcranial direct current stimulation, oftentimes the goal is to modulate a particular behavior or a particular disease state. The problem is, like I mentioned, transcranial direct current stimulation is usually applied to particular brain regions. But behaviors, diseases often localize much better to networks than to particular brain regions. So if we now know that you can modulate entire networks with tDCS instead of just particular brain regions, you can potentially have an even greater effect on those behaviors or those disease states. Another point is that a lot of the brain regions that are abnormal in disease are too deep to be accessed with superficial tDCS. But those deep brain regions have networks that extend up to the cortex. So by stimulating those cortical regions that are a part of that network, you can potentially modulate deeper brain structures that are really important for disease. So now that we know that the brain operates in these networks and that we can stimulate these entire networks, it opens up lots of new kind of exciting possibilities for modulating brain function. Lots of behaviors, lots of cognitive functions are really associated with networks. And so this technology, this kind of application of this technology really opens up some exciting avenues. One of the things that we're starting to investigate is modulating networks that are associated with particular disease states. So for example, in disorders of tremor, for example, oftentimes the abnormal regions are deep in the middle of the brain. And so one thing that we're trying to do now is to stimulate the cortical network that's connected to those deeper structures in order to improve some clinical functions such as tremor.